Welcome back. We have finished heat conduction, and now I'm going to move on to the wave equation. And for the wave equation, we're not going to be looking at a rod anymore. It's now going to be something that could move like an elastic string. So the way I like to picture this, let's write this out. I'll make the string orange here. An orange string. I should only draw it like this. It's fixed on the ends, as you can see. So this end's fixed. Well, we're doing fixed ends. This end's fixed. But let's say we pluck the string like in the middle here. It's going to look something like this. Comes up, comes down. Some kind of wave propagation, right? I don't know if you've ever taken like wave physics. But same thing, right? You've probably seen the wave equation if you've taken wave physics before. You've at least seen the form of it, which can be written very similar to the heat equation, actually. It's alpha squared once again. Obviously, the constant means something else now. I'm actually not entirely sure what it is off the top of my head. But it's a constant. In the math world, it doesn't really matter. This is a math video, of course. And the only difference with the wave equation is that instead of u of t, it's a second partial derivative with respect to time. So, here's the wave equation. As you can see, it's pretty similar to the heat equation. So, to solve this problem, we do the exact same thing that we've been doing. So let's go ahead and let's read it. Consider an elastic string of length L whose ends are held fixed. The string is set in motion with no initial velocity from an initial position f of x. In each problem, so in problem 1, carry out the following steps. With L equal 10 and A equal 1. Oh, parts B. Okay, well, I'm not doing part B through E because those are graphing problems, so I'm not going to worry about those. And E I'll kind of explain. So, basically what's happening. Someone's holding the string up like this, and then they're letting go. And we want to be able to quantify that motion. It's a perfectly elastic string, no irregularities, of course, symmetric, all that good stuff. So, it's the same idea as the heat equation, just the string. So now let's take a look at our boundary conditions. If we have fixed ends, right? So, whoops. So we have u of 0, t at the first end is 0, and we also have t is 0. Oh yeah, and by the way, in this case, u does not stand for temperature, obviously. It stands for, like this display. Oh, it says it right here, displacement from the given initial position. So our initial condition was right there, f of x, which is u of x naught is equal to that right there. Right, man, I don't feel like writing that. 2x over L, we have 2 times L minus, I'm going to multiply that in. Oh, that's 2L over L, that's 2 minus 2x over L. Right, this is from L over 2, this is from, now the length we're given is 10, so I could plug that in there. Let's just leave it like that for now. It doesn't matter. Oh wait, actually, we're good with keeping it as L. Because if you notice, it says let L equal 10 for part B through D. Because it wants us to graph it, so it has to give us a number. We're just going to use length L. Alright? Okay. That makes sense. I like that better, actually. So, keeps the math a little bit simpler. Step 1. what do we know to do? Oh, wait, first of all, oh, I almost forgot. We have another, so we don't just have one initial condition because for this problem, because we have an initial position, but we also have an initial velocity. Now in this case, it's being held up at this point and then being let go. So the initial velocity is 0, right? Before it's let go. So initial velocity would be 0 throughout the whole thing. Right? So like you can think of this, I can label these actually. This is the initial position. This is the initial velocity. At time 0. Okay. So let's go ahead and separate the variables of the wave equation. First time we're doing this, right? Alright, so we have alpha squared uxx equals utt. Uxx is equal to x double prime t. Utt, whoops, is equal to t prime xt double prime, right? Now, remember, we define u of x of t as being x to the x, t to the t, just like the heat equation. That's how we're able to say this. And then the next step would be to plug those right in. X double prime t equals xt double prime. We want to get the x's on both sides here. Now, once again, with this problem, as you can see now, we're probably gonna have, we are gonna have 2 second order problems, but we want to get the separation constant with the t's still. So we're still gonna divide this by alpha squared. So I'll move that x over, move that t over, and the alpha squared. And to find our separation constant, I'm still using positive lambda. It is very typical, I believe, for the wave equation that textbooks will use negative lambda, something along those lines. I like to use positive lambda for everything that I do. Just stay consistent. Now, if you're using like a boundary value problem table and it's based off of negative lambda, then obviously use negative lambda. But I like to do the problem all out by hand, so I just stick to lambda. Okay, so this will give us 2 ODEs. I'm sorry, yeah, second order ODEs. And then this alpha squared lambda t equals 0. And as you can see here, we have 2 second order ODEs. Okay, let's continue on. Step 2, boundary value problem. We know how to do this, right? Let's start by writing out we're going to use this original one without the alpha, obviously, because we won't be able to solve it with the alpha. I guess we could. Remember, for the heat equation, we always solve the second order homogeneous ODE. Oh, I know exactly why we use this equation. It just dawned on me. Remember, our boundary conditions are based on x. When x is 0, when x is L, the displacement 0. We don't have anything for time. Well, obviously we have initial conditions, but we don't use initial conditions for boundary value problems because it's not on the boundary. So yeah, we have to use this one. Makes perfect sense. See, I'm justifying myself now. Okay, perfect. Let's start with greater than 0. Yeah, lambda would have to be some mu squared. That makes it positive. Move that over, solve the characteristic equation. Write the general solution. That's just your standard second order general solution. E to the negative mu x. These use our first initial condition. C1 plus C2 equals 0. So then C1 equals negative C2. Plug that into our equation here. Looking at this, we have only trivial solutions, right? Because if we were to take out the, well, let's take out a C2. If mu is equal to 0, then we look at x up here. Excuse me. Then C2 would be equal to 0. Because you see we would have C2, this is 1 minus 1 is 0. If C2 is 0, C1 is also 0 based on this, so then x is 0. So it's only trivial. Now let's continue on. Equals 0, so lambda equals 0. Remember, this is really only a case if we have Newman boundary conditions. You might have started to pick up a pattern of this, so I already know this is only trivial, just like the last one. So I'm going to do it really quick here, just to show you. I don't even have to do it to know. Right? Take the derivative. Sorry, just plug in 0 for x. I'll rewrite this down. Second boundary condition. That is C2 times L, which tells us C2 is also 0, C2 is 0, C1 is 0. Only trivial. Then the last one clearly has to be the correct case. Use our shortcut. First boundary condition. C1 equals 0. That leaves us with this. Next boundary condition. Now, this is obviously non-trivial because mu is going to be non-zero, meaning that C2 can be, excuse me, well, alright, well, in order for sine of mu L to be 0, mu L has to be n pi. So then we can set mu as being n pi over L. Sorry, you know what? I kind of explained this bad up here real quick. This right here. If the only way for this portion here to be 0 is if mu is 0, right? If mu is 0, we're left with C1 plus C2. Now we know C1 is equal to negative C2. Negative C2 plus C2 is equal to 0. That is the reason why, so I can erase this. Sorry, I kind of confused myself there. It's been a while since I did this. I kind of took a little bit of a break in between videos. Right? Now it all makes sense to me. I had a little forgetful moment there. Back where we were, obviously, what does this make? What makes this 0? Well, this. We get a value. Plug in mu up here. We would get, sorry, not there. Here. We would get an answer. But we're using this one here. So our eigen value, eigenfunction, that's what? Negative n squared pi squared over L squared. Eigenfunction is x to the n equals c to the n sine of mu n, so that's n pi over L times x. And these are both so on. Bam. Let me make sure that's right before I continue. Yeah, it looks right to me. Alright, step 3. This is going to be a little bit different. Solve for t, right? So remember, we had this here. Can move that whole right side over. And then we plug in for lambda here. Whole thing becomes negative. Oh, sorry. Now, I'm going to solve the characteristic equation. This is going to become r squared equals becomes this here, right? And you take the square root. That's going to become plus minus alpha n pi over L imaginary portion, right? And then that becomes right using the shortcut. Right? No e components of that one. Step 4. Fundamental set of solutions and general solution. So for this one, we have u of n and x of t. Remember, u is equal to x of x, t of t, so we're going to multiply them together. Figure out what x of n is, cn sine. Here's what I'm going to do. Since this is two components here, And you see how we have sine and a cosine? And this one up here is a sine, and they're being multiplied together. What's going to happen is, let me write it out. Let me write it out. This really should be to the n. Something like that. I'm going to call on something else because I want to stick to my notation in the notes. Do something like this, just for now. Just to show that that's a different constant. Based on n, though. I'm not fitting all that. Okay. We can multiply the constant in, and then we're going to end up with two new constants. Now, I'm just going to, because I want to follow my notation that I have in my notes so I don't mess and make any mistakes while I'm doing it. I'm just going to call C sub n times f of n C of n. Should just stay C of n. But it is a new constant. It's f of n combined with C of n. Just so you're aware. So, in case you're confused. And we'll call this one D. So it looks like this. And then, obviously, we're not done yet because we have u of t, which is fantastic. Actually, no, we have un of t. We now want u of x of t. That's just the same thing, but putting a summation on it. So I'm just going to copy, paste, shrink it down. Perfect. And I should label that as general solution. Now, that's for the displacement. Now remember, they also gave us an initial condition for velocity. So we have to actually, now that we have this, take the first derivative with respect to time. I want to move that sign to the end, by the way. I'm just going to move this all over. Pi t over L. D sub n alpha n pi over L. I'm going to run out of space. Times sine right, I move this over Move this over to here. Now we use the initial conditions and the Fourier series for step 5. So we'll start off with the first one. We know the first initial condition is f of x, which is equal to, we had a piecewise function. Okay, I have it written down here, so it's that. Of course, we have bounds, two different bounds here. Okay. Now, plugging 0 in for t. Let's take a look. Plug 0 in for t. We have c of n plus 0. So that's just c of n times that. N pi. Well, that simplified a lot, didn't it? And then we also have to do it for the other one. So these are our two things that we have. This one was 0, started at rest. I know it starts with d of n because the other one's going to be 0. Because now x is 0. Oh, wait. Excuse me. I'm looking at a u of t. Wrong one. So sine, cosine. This one goes to 0. D sub n alpha n pi over L. Times the same thing that's up there. Okay. So then we know that this is going to be, they're both Fourier sine series, right? We have well, I don't know if it's considered two separate Fourier series. I don't think so. No. I mean, no, because okay, so all this is doing is still one Fourier series. So, okay, I see. I get it now. What we're doing is we're finding c sub n and d sub n. So what u allows us to find is c sub n, c sub m. What u of t allows us to find is d sub n, and they both go into this general solution right here. This is what really matters right here. Okay? I get it now. So we have a Fourier sine series, which is odd. So that tells us that d sub n and c sub n are both going to be equal to L to L f of x sine n pi over L times x, where this is an odd function, sine is an odd function, that times that is an even function. So obviously it's going to be integratable, or else we wouldn't have the solution, right? So let's find d sub n. Oh boy. Oh boy. This. Oh boy. Okay, so I have it. I have the piecewise function written up here on my screen here. You guys can't see it, but actually no, d sub n should be pretty easy to solve for. right? Wait. Because we have, oh yeah, I forgot. I don't think we ever did a problem like this yet. When we have this extra term in here, we'll definitely be seeing it from now on. But what you do is you basically are going to multiply the, the constant here by that value. If you watch my Fourier derivation video, you will understand why. That is equal to 2 over L, because if you can go from 0 to L, this is an even. Oh yes, because it's the integral of an even. Oh my god, I'm like looking at this. It's odd. I forgot. Yeah, 2 over L from 0 to L. F of x times sine of n pi over L x. Now this is obviously very easy because we know that the initial velocity is 0, so we're taking the integral of 0. So instantly I can tell you this is equal 0. Don't even have to write the rest out. So we don't need this one, nor d sub n. Let's go to, I need more pages here. We're going to go to c sub n, which is unfortunately going to be very long integration. So be patient with me here. Oh boy, I don't want to do this. This is probably the hardest one we're ever going to have, to be honest with you. Just because it's long. Okay. C sub n. So we started off. I'm gonna where is it? We have 2x over L from 0 to L over 2. Actually, here's what I can do. Never mind, it doesn't let me do it. Actually, I can do this. Is this it? Yeah. Oh, crap. You can pin it, I think. Yeah. Then they updated that. Okay. Okay, so C sub n is equal to, I'll pull out that 2, that's going to be 4 over L squared, integral 0 to L over 2, x sine n pi over Lx plus 4 over L over 2 to L sine of n pi over Lx minus, we have the last one, it's still 4. Now this one's going to have a L squared like the first one. That x stays on the inside, unfortunately. Just like the first one there. Sorry. Now this one's going from L over 2 to L as well. X sine n pi over Lx. That's the full thing. So we can go ahead. Both integrals are the same. So we only have to really write out the integration by part thing once here. Sorry, du. Would that be negative? Yeah. Yes, so now I don't need this anymore. Now we have 4, and I can pull out that 4 over L squared as well. We just have to multiply everything but in that second term by L, I think. So this will leave us with oh, this is a really unfortunate problem. I'll show you why. Oh no. I'm going to be forced to actually do every integral out. Because it's L over 2. Wow. Wow. Okay. Oh man. This is rough. Let me just do it. Let's just start getting the work. I'm going to pull this out. UV. From 0 to L over 2. Plus integral, so I'm going to pull it to L over, well, it's minus the integral, but the negative cancels out. This is going to take up multiple lines. Yeah, that's enough for that line. Okay, well, there's that one. Now, the second line, we're going to keep going. I guess this is going to, because this is negative cosine, the integral of that. Right? Yeah. It's going to be minus, and then we're going to go ahead and we took out a 4 over L squared from the whole thing. This is going to, you know what? I'm going to do some rearranging. I'm going to move this over to here and this over to here. So I'm going to do this next part first. So to continue with the integration by parts. Yeah, now this would have to be minus. You have 4 over L squared times, so that's still there. It's going to look exactly the same. The inside's going to be exactly the same, so we can just go ahead and do this. Just keep copying it down. The bounds are different though, that's the only difference. Now, this kind of sucks. Well, let me do the last part first. We have plus, I remember it was 4 over L, integral of sine. And this one was from, same thing, L over 2 to L. Okay. So there's that. The reason why this sucks is because typically we go from 0 to L, and then this integral would cancel out because sine of n pi is 0. This integral would cancel out. But unfortunately, it does not. Oh, man. Oh, man. So, I mean, some of it's going to go to 0. See, this top one here is going to go to 0. What else is going to go to 0? Nothing, right? That's it. So I'm not going to write that down on the next step. I'm going to move on here. So we're going to end up with 4 over L squared. Oh boy, this might be kind of a long video. I'm going to try and hurry up here. I don't want a straight copy from my notes because I sometimes make mistakes in my notes. Cosine n pi over 2 plus L squared over n squared pi squared sine n pi over 2. Right? Because we have L squared over 2. Bam, bam. Plus, and then, you know, if you make that 0, that's just, did I forget that term? Cosine of 0 is 1. Oh, the x is there makes it 0, so then that's it. Yep, we're good. So then plus L over n pi. Oh, wait. Yeah, we still got to integrate that, right? Actually, what I'm going to do here, because I don't want to integrate this. I don't want to integrate those two things into here. I want to skip a step, and I want to do them separately. So let's say looking at integration separately. I do this trick quite often. You know, I like to break things up. So we're gonna, when I do that, oh man. We're taking this section here and this section here. Integral of cosine. We know that the integral of this, regardless, is going to be sine. And for this case, we're either going from 0 to L over 2, or from L over 2 to L. So that prevents us from having to write those down at the moment. So then we can just go ahead and evaluate those. So this is plus. This is from 0 to L over 2 case. We're left with L over n pi. Oh, wait, I'm doing the wrong. Wait, no, we're good. It's L squared over n pi. All squared, isn't it? L squared, n squared, pi squared. Okay, L squared, n squared, pi squared. I'm sorry. I already did that second. Oh my lord. Okay. Well, good. We already did this one. This one's already been done because it's right here. I was copying my notes. That's why I didn't know where it came from. Okay, we look at the next we'll look at this part here. That part's pretty easy. That's minus. Yes, I'm gonna erase this for now. It's minus L squared over n pi cosine n pi plus L squared over 2n pi cosine n pi over 2. Does that make sense? Oh, it's from L over 2 to L? Is it really? Oh, yeah, it is. Okay. You plug L in, yes, I agree. Plug L over 2, yes, I agree. Okay. Then we have plus. That's a bunch of squares. So L squared, n squared, pi squared, times sine n pi, minus L squared over n squared, pi squared, sine n pi over 2. Probably, yeah, n pi over 2. L's cancel. And we're still not done yet. Just into that section. Let's go over to the next section. We have this other section, 4 over L. Two. Yep. That's this section right here. I see some things that are going to cancel here. This is going to cancel with this. Where the hell is it? I know I saw it before. This one. And this one. Does this cancel? Am I seeing things? Those definitely cancel. This is obviously 0. I didn't even see that before. Ooh, these cancel. I believe. Oh, I see what's going on. There's a negative here. This negative gets multiplied into here. So we have this with this negative one. We have this negative one. That's minus 2 L squared over n pi. And you can see here, you got to take into account these L squares here, and this is an L. If this is divided by L, L cancels. If this is divided by L squared, L cancels. So we have minus L over 2 n pi minus this, so those will cancel. So I'm kind of, I know I'm moving kind of fast here, but these will cancel. Yeah. Oh, wrong one. These 3 will cancel. Ooh. Okay, and then I think that's it. Oh, but the other cosine that's there, because that's gonna be. Oh yeah, that might no. Yes, that will cancel too. Holy crap! This is gonna cancel with this one. See why? Because this divides by L squared. Divides by L. It's positive 1 over n pi minus 1 over n pi 0. So did every term cancel? Oh wait, these don't cancel. So we're left with 4 over n pi n squared pi squared. 4 over n squared pi squared times sine n pi over 2 plus 4 over n squared pi squared sine n pi over 2. Interesting. So that those combined, you know, that's just 8 over n squared pi squared times sine n pi over 2. Yeah, so that kind of sucked. So that's our C sub n. Is that. So then we can go ahead and write out our u x of t, because we know d sub n is 0. So that leaves us with. Actually, let's make our life easier. Let me copy all of this. And this is 0. So then we're left with sine n pi over x, L over L, sine n pi over Lx. Actually, I'm going to put that on the end. We're left with a what? 8 over, I'm going to pull that out, 8 over pi squared. N equals 1 to infinity. 1 over n squared sine n pi over 2 times cosine alpha n pi t over L times sine n pi over Lx. I just moved that over to there. Right. Sorry, that looks bad. That's our answer. That's the displacement anytime t at any position along the length of the string. That's what this represents. Okay, really quick, I have this down here. I just wanted to show this, what happens here. So what we're looking at here now is we still have two fixed ends with initial position, but this one just is going to be starting from the equilibrium position with an initial velocity. So what's going to happen is the boundary conditions are just going to flip. Right? So we're going to have boundary conditions of u of 0. Sorry, not the boundary conditions are going to flip. The initial conditions are going to flip. I'm not sure what I said. We have initial position is going to be 0, but u of x of t, x0 is going to be this right here. Oh no. Copy. Bam. That right there. Just the last problem. So now, what we're gonna do is, this is the same. This is going to lead the exact same answer as last time. Everything. Steps 1 through 4 are exactly the same. 1 through 4 are the same. Because, the boundary value problem doesn't depend on the initial conditions until step 5 with the change in initial condition. I'm trying to get this video under an hour. Change in initial conditions. So, let me go ahead and write down the general solution again. And here it is right here. So what we're solving for now is it the same? Yeah. I need you to do the t as well. Should just copy that whole thing. Right. That's still the same. The next step is what's going to change. So, as you can see, this is really easy. Right? It's just going to flip. It's just going to flip. B sub n c to the n, same integral. But now, sorry, I mean d sub n. But now d sub n is going to involve the piecewise function, and c sub n is going to involve 0. So c to the n, so in this case, c to the n is 0, and d to the n is just going to be the answer to our integral that we had before. Bam. So now, we go ahead and write out the general solution. Sorry, u of x of t, 8 L over alpha pi cubed times from n equals 1 to infinity, 1 over n cubed sine n pi over 2. That's that right there. Is that cubed? Where is that? Why is that cubed? It's pi n. It's alpha n pi over L. Did I write it down wrong? Alpha n pi over L. No, I did not write it wrong. Oh! Remember when I said in the last problem, when solving for d sub n, you have to multiply it by this? I'm like, where am I getting these numbers from? So, yeah, this is actually d sub n times n pi alpha over L. That's where this L comes from. That's where this alpha comes from. That's where the pi cubed and the n cubed comes from. Okay. Now it all makes sense. And then we're going to have the cosine. No. Sine times sine, right? Why do I have that written there? It's 0. That should be it right here. I did it wrong in my notes. Okay, yeah, that should be the answer. I don't know why I have a cosine term in there. It goes to 0. I must not have been paying attention. Yeah, no, that's correct. Okay. There's xt. So that's the answer to this one. So you see, you have to keep in mind this little bit right here next to the d sub n, because going back up to here, sorry, over here, we have this extra term in our in our Fourier series. This has to be multiplied over on the other side with the d sub n. That's again with the d sub n. When you're solving for it, you solve for this. This becomes like the coefficient. That's how it goes. Like I said, watch my Fourier series coefficient derivation video, and you understand exactly what I'm talking about with that stuff. So here's the answer to this. I have one more wave equation video. Wave equation is pretty simple. You know, there's not many more examples we can do for this really. Kind of the same as the heat equation, just a different formula. That's really all it is. But I'll look at one more problem where we have a fixed end and a free end. So like that end's not staying still. It's gonna have a value. So I will see you for that video.